Okay, so welcome again. So again we have good and simple question asked in GATE examination. So GATE AC. Okay. If H is given like this, Hx Ax roof minus Hy Ay roof represents the magnetic field in a transverse plane of an electromagnetic wave traveling in G direction. Then what is the electric field in the wave? That means it's very simple. Given H, you need to find E. So you have a transverse plane, something like this, and say you have direction of propagation is transverse to the transverse plane. So transverse to the transverse plane means here transverse means perpendicular. Okay, so wave is propagating along Z. When wave is propagating along Z, along direction of propagation, I can take wave vector K. Now I have my transverse plane here. So this guy is my transverse plane. So you have the wave, of course, the wave says traveling all the way like this. Now H is defined, that means you see Hx component you have, of course, it is polarized in x-axis, and this component is polarized in y-axis. So if it is my, say, x-axis, this is my, say, y-axis. So of course x cross y is G. And of course you have both H and E involved on the transverse plane. If I take E cross H, if I take E cross H, this happens to be on the transverse plane, and the resultant stuff is transverse or perpendicular to the plane containing E and H, and that is what the power flow. This is of course power density. So power flow, or the density, the power flow is along direction of Z or K, and that's what given to you. Okay. Of course, this is based on Poynting's theorem. So how do we tackle down this problem? So you have H and how to find E, because I know very well, already we proved this. So already what we proved is, remember this, we proved this one, that is, if I take a ratio of these two transverse components, Ex over Hy is eta, and also from other Maxwell's equations, we understood that minus Ey over Hx is equal to same eta, of course. This is what we proved already. So j omega mu by sigma plus j omega epsilon. Just refer your khatas, your notebooks. We just proved this stuff. So positive Ex over Hy is eta. This is nothing but negative Ey over Hx. Of course, Ex, Hy, Hx, they are transverse components. And of course, Ex, Ey are transverse again, Hy, Hx are transverse. So therefore, often we say that TM wave, the propagation of TM wave, transverse electromagnetic wave, is transverse, means perpendicular to a transverse plane, containing transverse components like Ex, Hy, Ey, Hx, and are transverse to one another. Saying again, direction of TM wave is transverse to a transverse plane containing transverse components and are transverse to one another. All right. So I know this Ex, so it's given here Hx, Hy. Just express Hx, Hy in terms of, E's. Okay. So from this I can say that my Ex is equal to eta Hy. So I found Ex, and also from this, so from this I can find Ey is equal to negative eta Hx, where eta is equal to what? Intrinsic impedance of the medium. Okay, so just plug in. So anyways, H and E will have same form. The only change is in terms of amplitudes and phases. Otherwise, they always exhibit same form. So my general equation is this: E is equal to, I love to take in general case Ex, say Ax roof plus Ey Ay roof. Okay, this is nothing but now what is my ex here? Ex is eta hy. Okay, so this is like okay, I'm just taking like this. Just okay, this is ey is minus eta hx. Okay, so minus eta hx, and of course I have here. So this is like ax roof, and this is like ay roof. How do you think is this correct? So ax equal to, of course, we obtained eta hy, and ey is equal to minus eta hx. But one thing you have to note down that is this direction. Okay, ax is given to you, so ay is given to you like this here. So my ay I can do this one as plus hy negative ay roof. Okay, so plus hy negative ay roof, and if you solve it, if you put that stuff, you get minus eta. So you must get hx ay roof plus you must get hy ax roof. You know very well. So E must be perpendicular to H, and this is of course perpendicular to K. So you just follow this right hand rule, EHK, solve for it, of course you'll get this. Already we have done a problem based on this, so just compare with this with the stuff and you must get the answer. So there is no big deal in that. Okay, so this is one, and I'll take one more. Another question asked in GATE. This is direct question. There is no twist, nothing in this question. This is straightforward. The magnetic field intensity vector of a plane wave is given by, okay, H is varying both in space. H is varying both in space as well as time. So Hxyzt is 10 sine, of course, you have this 5000 t, so omega is given to you. And this is like beta. Okay, so wave is traveling along negative x-axis, or wave is propagating in space along negative x-axis. So the given wave equation is one-dimensional wave equation. Okay, of course here we are showing all the space 3 dimensions, but of course the wave is traveling in negative x-axis. Okay, because you have something like this. So you have 10 sine, you have something like omega t plus, let's say, of course, I have beta x plus some initial phase. I have something like this. And of course, so this H is polarized. This H is polarized and along y-axis. Our direction is y. So now this argument, you can write it down like this: omega t minus beta of minus x plus some initial phase. Now this indicates what? The wave is happily traveling along negative x-axis. Okay, this is negative x. So that's, I mean, so this must be straightforward. Okay, so the wave is propagating with a phase velocity of, so it's very simple. I know how to find this. Anyone? So let me give some 1 second pause. So meanwhile, you get this answer for me if you want. So anyways, the phase velocity, I can find it out. Omega over beta. I know this form already. So omega is given to you as 5000 radians per second. Okay. So omega will tell you what, how fast your electromagnetic wave is varying in time. Okay. So therefore, you are multiplying time again. So radians per second multiplied by second is radians. This talks about phase again. So beta is given to you as 0.004. So it is, okay. So you get 1.25 multiplied by 10 to the power of 7, and of course meter per second. Okay, the units for omega is what? Units for omega is radian per second, and units for beta is a radian per meter. Okay, so you get meter per second. All right. Now what do you think? Because if an EM wave is traveling in free space, this is say my free space or vacuum. If EM wave travels in free space, now you can approximate like this. The phase velocity of the EM wave in free space or vacuum is given like this: c sub naught 3 multiplied by 10 raised to the power of 8 meter per second. Okay, or this could be free space, this could be free space, or I can take vacuum. Electromagnetic waves loves to travel always, okay, either in free space or vacuum, because they are lossless. Ideal cases is this. So but now you are experiencing a slow, a phase velocity of a wave is now slowed down in a medium. So because 1.25 10 to the power of 7 is less than this. So what could be the reason behind this slow down? Because of, I mean, what could be the reason behind the velocity slow down? It's traveling in some medium. So now if you're interested further, you can go and solve it like this. So how do you do this? I can find it out. Like that means we know very well refractive index of a medium is highly responsible in slowing down velocity of a traveling wave. Okay, so this is my medium. Okay, my medium is this. Now EM wave is traveling all the way in the medium. So now I could say a refractive index of the medium. I know already we proved this one, right? So velocity of light or EM wave in free space or vacuum divided by the velocity of wave in this medium. So I have 3 10 to the power of 8 divided by, yeah, what is V obtained now? Of course, V means of course phase velocity. So you have 1.25 10 to the power of 7. So this is equal to what? So this is nothing but say 24. So refractive index is 24. Gone, it's too much. Refractive index is very, very high in this case. If you take for free space, n is approximately equal to 1. Refractive index is 1. That means phase velocity and velocity of light both are same. So therefore n becomes 1 in free space or vacuum. So therefore happily young wave will travel with this speed. But you take any general media, or media is plural form of medium. So media. So whenever you encounter EM wave is traveling slow in that medium, then you must understand that refractive index is greater than 1. Yeah. So therefore it's slowing down. Okay, it's slowing down. All right. So already we understood that when a wave is entering from one medium to other medium, this is say medium 1, this is medium 2, and you have some refractive index n1 and refractive index n2. If n2 is greater than n1, the wave, you will see the wave, for example, this is the case. A wave has something like this. The moment it enters here, the wavelength will decrease like this. So you have, the compressed form of wave motion like this you have. Now this doesn't mean that frequency is changing. You would think this way, the wavelength is decreasing here, so frequency is increasing. No. So there is no increase, or there is no change in frequency when you go from one medium to other medium. In this case, the only thing is the wavelength is changing. And also when you see the compact form of waveforms like this in the other media, then you would think that velocity is decreasing, and that's a sign. And I think already we observed the animation of this. So please don't forget this one. It's very important to make a note. Okay. Thank you very much. And again, enjoy your rest of the day. Bye for now.